Hi, this is the introductory chapter for computer organization class, and we will review key concepts. And before that, this is our textbook. It is computer organization, and for the famous authors David Patterson, John Hennessy, and Morgan Kaufman. Um, the important things we have reviewed this in the introductory class. The important things is that we would like to discuss key or let's say introductory concepts. One of them is the we need to point to the computer revolution, and this computer revolution, um, basically, computers and digital systems, they are everywhere in our lives, in the automobiles, and the cell phones, um, in the internet, the search engine, etc., etc. So, uh, to sum up, computers and computing systems are pervasive. They are in everywhere in our lives. Um, there are different classes of computers and digital systems. You can classify them to desktops, servers, embedded systems, and basically you can say that the servers are the faster machines, the high performance machines, the desktop and laptops, kind of the personal usage for um, students uh, and small organization. And embedded systems, on the other hand, and embedded computers are in are those digital systems that are in a system which is not called a computer. So, for example, your microwave and washing machine, the automobile, whatever digital system is there, is considered to be an embedded system. The point is, um, all these are different classes of computing systems where you can look at the servers as the high-end, fast number crunching machines. Embedded computers or embedded systems are those in systems that help um, sort of automate um, the operation of the device. It adds to it the automation. It might add to it some artificial intelligence, etc. Okay. Um, Needless to say that the market for um, uh, the processors have been going through an exponential growth, and obviously propelled by the need for electronic devices, PCs, etc. So, you can see the need for understanding the computer system. Okay, and in this course, we discuss how we translate high application programs into some kind of machine language. We did this in earlier courses, like the assembly, but we're going to point to this one more time. We are going to study this hardware software interface, very important concept. And this is your basically above that you have the software world, below that you have the hardware. So that's interfaces is important, and some people refer to this as the instruction set architecture, and that's the interface between the hardware and the software. We will look at key metric for performance, and in this course, speed or time, CPU time is the key metric. But I must say that in actual systems, people now pay attention to other metrics, and they are really key metrics. For example, energy consumption, and it is critical for devices that are sort of implanted in the human body, for example, or that are placed in hard to reach areas, like for example, outside cities, where they kind of do some monitoring or sensing. So these for these systems, energy is very important. Sometimes a metric is used as the cost. Okay, you want to have a computing system with decent performance, but with the lowest cost, so that it can be sold in volume numbers. Okay, so in this course, however, we will refer to the performance uh, uh, to to just the CPU time, and we will limit that to the performance just to the CPU time. Okay, of course, we are going to focus on how hardware designers can improve the performance, that is CPU time. We're going to talk on some para- parallel processing at the end of the course. Now, if you want to improve performance, and by the way, this applies to CPU time and energy and power and all that, you really need to look at the entire picture here, and that includes the algorithm that you are running, includes the software side, programming language, compilers, and the processor and the memory system. Okay, while we are going to focus on this, right, in this course, and the I/O systems as well. But in reality, people have to worry about the entire stack, which impacts the performance. Now, if you look at when we write programs, those programs typically in C Sharp, C++, Java, they are referred to as application software, and they are kind of translated by compilers and assemblers to some kind of machine language, okay, which this machine language drives the hardware. It drives the hardware. So this is our application software, and then you have system softwares like the compilers and the assemblers, which translate to machine language that drives the hardware. So this is kind of your the way you look at how things managed in the computing system. Okay. In terms of hardware, we need to worry about the processor, the memory, okay, and the I/O controllers, because they kind of drive the or they are our hardware. Now, of course, as we mentioned in the earlier slide, that you have this high-level language translated to assembly, and assembly translated to machine language, and this is where your hardware understand this language. The hardware does not understand C or C++ or Java, or even assembly. It rather understands the language of ones and zeros, and from there, okay, to here, you have to kind of apply this algorithm to compilers and assemblers, so that you get ones and zeros. One thing interesting is that in the early years of computers, they used to program computers with ones and zeros. Of course, it got very tedious and boring, so people invented assemblers and compilers to make it more human friendly. Okay, so this is kind of your level of program code, if you will. High level, assembly language, and machine language, which is very straightforward and directed to the hardware. If you look at the computer system, the major components of any computer system, you can see the computer system consists of inputs, like for example your keyboard, okay, and output, like for example your screen monitor, okay. Another input, by the way, is the mouse. Another output is the speaker, for example. Okay. Inside the computer system, you have the processor, which consists of a control section and data path section. And control section sort of orchestrates how the things happen inside your computer system, and the data path basically takes in data, crunch the numbers, and produces the results. Okay, in this course, our focus will be on the data path and control. So basically, this processor, okay, side. So this is where the processor, which consists of data path and controller. And we will also, at the end of the course, visit the memory. Okay, so this is the memory, right? Right. So the memory basically saves the data that comes in from the input and saves the results that is going to the output. Okay, so the processor and the memory will be the focus of this course between our hands. Okay, so here more of a picture of the anatomy of computers. So the input and output devices. Okay, and then what we will do is that we're going to talk about the CPU, both in terms of the data path and the control, and we're going to talk about the memory system as well. Some imagery of old processors, and you can see how they are organized. Um, and we are going to uh, talk about in the coming lectures about the instruction set architecture, which is the interface between the software and the hardware, and kind of applies the knobs required to drive the machine underneath in the hardware. Um, Technology trends, you can see that how the bits capacity for DRAM technology versus years, and this is the growth is exponential. Notice that the y-axis is logarithmic. Okay, and the point is that we are packing more transistors per chip every single year, and in fact. Here's this graph here. If I can go back here a little bit, this graph is driven by something known as the Moore's law, and Moore's law states that the number of transistors packed in an IC increases or doubles every 1.5 years. Okay, so that's one of the fundamental laws that in computer hardware. We're going to need to understand the difference between response time and a throughput. And basically, the response time, it is how long it takes to do a task. That's the response time. And while the throughput is the total work done per unit time. So response time is really very important if you are dealing with real-time applications. So for example, if I'm calling somebody in a different country, and we are having a conversation, then the response time is very important so that we can have a meaningful conversation. If it takes hello from me to him a minute, then the response time of this let's say phone system or internet phone system is not good for uh, live or real time application. So response time, it is critical for um, the real-time applications. How about throughput? Throughput is really important metric when you're having lots and lots of product to complete. So for example, if you're having a bakery, right, and in the bakery you are baking breads, and you want to do as many of pita breads as you could. Then you worry about the throughput. You know that every pita bread will take this almost the same time if you do one piece or you do a million of them. Okay, but in this case you're not really kind of concerned of the response time. You are really concerned of how many you finish of these pita breads per second or per minute. So tasks per minute, per hour, okay, is what we care about for throughput. So throughput, as I indicated earlier, it leads itself. It's a metric for processes which kind of deals with large number of items, large number of data. So you're concerned about the volume rather than the response time is concerned about the quickness, the speed. So response time important for real-time application. Throughput is important for if you are doing high performance for crunching lots of instructions, lots of data. Okay. All right. Okay, so in this class, we will define performance as 1 over the execution time. So, for example, if you have let's say time to take to run a program 10 seconds on A and 15 seconds on B. So the execution time of machine B over the execution time of machine A is 15 over 15 seconds over 10 seconds, and that gives you a factor. And that is really, as you can see, this is how fast machine A compared to machine B. A is 1.5 times faster than B. Okay, so that's the definition that we will use. That the performance is 1 over the execution time in this particular class. Okay, we have other definitions of elapsed time, which includes all aspects, includes processing and IOs and operating system overhead, idle time, etc. But really, we're going to focus in this class about CPU time. How much time it will take the CPU to crunch your program, and this is what we are going to discuss later on. But let's just before doing that, let's just take a look about what we define as the CPU clocking. In the CPU, we have a signal called the clock. And the clock is a signal which organizes the activities in the system. Okay, and so you would want to have some signal which kind of synchronizes or organizes the activity. So the synchronization happens with this clock signal. The clock signal has a period, okay? 1 over this period is the frequency of the clock, okay, as a definition, all right? And this clock signal, we will try in this period to finish and execute as many things as we can before we go to the next period, okay? In general, the shorter the clock period, or the higher the frequency, they mean the same thing, the better the machine is. And I say in general because the performance of a machine, CPU time in this case, depends on other things other than the clock, the clock period or the clock frequency, other parameters as we will see shortly. Okay. So here, for example, shows that the clock period and how we compute clock period based on clock frequency. So again, frequency equals 1 over period, and period equals 1 over frequency. So these relationships are basic ones. Okay, we'll stop here and continue our discussion in the next class or the next part of the introduction. Thank you very much.